Chemical bonds are characterized in a variety of ways. Ionic bonds, for instance, are where the electron is transferred from one element to the other, and it's a plus-minus Coulombic interaction that holds the bond together. That occurs when an electronegativity difference is very large between the two elements. So if an element from one side of the periodic table bonds to an element on the other extreme of the periodic table, you're likely to have an ionic bond because the electronegativity difference will be large. Lithium fluoride is an example of that. Now, you can have bonds where the electron is shared more equally between the two. You could imagine a perfect sharing. For instance, covalent bonding is where sharing occurs, and chlorine Cl2 is an example where you have a homonuclear bond. That is, the electron has a preference for neither chlorine. Chlorines are identical. The electron has equal preference. There's an equal probability of finding the electron on either chlorine atom. So that bond is perfectly covalent, an equal sharing. But it's actually more likely that you'll have bonds between different elements. So there'll be a slight electronegativity difference between the two elements, and therefore a slight preference for the electron to find itself on one element as opposed to the other. So those are called polar covalent bonds. An example, hydrogen chloride. Here, the chlorine is the more electronegative element. So it draws the electron toward itself, and there's a higher probability of finding the electron around the chlorine. That gives the chlorine a slight negative charge, and the hydrogen a slight positive charge. So the hydrogen end of the molecule, slightly positive. The chlorine end of the molecule, slightly negative, because there's a higher probability of finding the electron around the chlorine. Now that partial charge separation that we denote by these partial negative and partial positive symbols gives rise to what we call a dipole moment, a charge that's separated in space. A dipole moment is a vector quantity. It has size, the size of the charge separation, and the distance between the two. So in this case, we draw a dipole moment vector from the positive to the negative end of the bond. Now, virtually every bond is going to have a dipole moment because it's very rare you find perfectly equal sharing of electrons. So if all bonds have dipole moments, it's likely that all molecules will have dipole moments. But there will be cases where the symmetry of the molecule allows dipole moment vectors to cancel. For instance, a perfectly symmetric linear molecule, a dipole moment in one direction will perfectly cancel the dipole moment in the other direction, and you'll have zero dipole moment for the molecule. There are other symmetry examples where that can happen. But by and large, you'll find molecules that have dipole moments that don't cancel, so the whole molecule will have a dipole moment that's the sum of the individual dipoles. And usually, the molecules will have a permanent dipole moment. Now this bent molecule here, we have an example of that. Water is a bent molecule, where two dipole moments for the bonds, HO bonds in this case, don't cancel out. And I can demonstrate the dipole moment in water because the dipole moment creates a charged end of the molecule that will be attracted to a charged surface. So let's look at that. What I have here is a setup for a stream of water. I'm going to bring a stream of water from this burette, and I'm telling you that if I have a charged surface and I can put a negative charge on this rod by rubbing it on this cat fur, a negatively charged rod will attract the positive end of water molecules. So I'll start a water flow from this burette, and now watch what happens to that water flow when I bring in a negatively charged rod. Look at that. The entire stream of water bends towards the negatively charged rod. The positive end of those water molecules attracted to that negatively charged rod. That's a very dramatic demonstration of dipole moments in molecules. So dipole moments occur when molecules have dipole bonds. Every bond has a dipole moment, and all those bond dipole moments do not add up to zero. That gives rise to this polar covalent bond, and it's one of the kinds of bonds that we understand on a spectrum from covalent to polar covalent to ionic bonds.